Share the screen. Okay, so we looked at autoencoders. We started looking at autoencoders. Now we're going to move on. We're gonna continue our discussion with embeddings. We're going to get into BERT a little bit, but the key word here is embedding, right? Remember the process is essentially a matrix multiplication. This is also called a vector projection, right? And then there's some kind of logic, as you saw, on whether we're using the same vectors, other vectors that are kind of correlated, etc. But we're using this information to train essentially a representation here, an embedding. So this black word here, word 4, becomes an embedding of size 256. Okay, so keep that in mind. So let's go now to word embeddings and BERT. So essentially it's the same idea. We're still trying to produce an embedding, a vector of a specific size that's capturing some meaning. Right, so I have a few notes here, and then I have like a write-up, like a blog post type of thing, and then we're going to get into some code. So today we're not trying to code the baby BERT. We'll leave that for another. Instead, I'll introduce more like Hugging Face kinds of things still, just to kind of motivate this idea. But keep in mind, essentially, BERTs, at some point somebody had the realization and they said, you know what? A BERT is just an embedding machine, a much more complex embedding machine than what we just did, right? So our autoencoder was simple, but ultimately it gave us a vector, an embedding. And now BERT also gives us embedding. So I'll talk a little bit about that and the history. But now, this is kind of like a BERT introduction. Okay, so I have you can see it. And I have I just have a few notes here that I want to touch on. Okay, so this kind of captures the idea, right? So now, just like before we had the autoencoder, now we have a BERT. I'm treating the BERT right now as a black box because obviously a lot goes into this, the same attention mechanisms, all that stuff similar to GPTs. But what's important here is BERTs now, they're not just a vector of 784 like in our previous autoencoder, right? We just had that one vector of 784. Here we have sequences of vectors, right? So we have batches of 32 where each batch is a sequence, let's say, of 40, and then each one of those values in the sequence can be a representation of size, let's say 256, right? So now it becomes this idea. So what's great about this is that we can represent language that way, right? So for instance, BERT takes a sequence of 512 tokens in this example. The first token of a BERT model is CLS, and that's there's special tags, this one, S, this closing S, the word mask, CLS, which indicates class, SEP, which indicates separator. So these are special symbols that can be used with the tokens in BERT when they wrote the initial BERT paper. Remember, that was coming from the Transformers paper. So you have help the princess, I think it says. You have this sequence, and then this in BERT comes out as also a sequence of 512, but every one of these is an embedding now, a vector of size 768, which is just numbers, right? However, because of the training, these numbers have useful information. This first one here, this green one, highlighted as green, is a vector of 768, but if you add additional layers, you turn it into a classifier, for instance, or something like that. That's the idea. Okay. Obviously, to train it, we're going to do pre-training, then fine-tuning of these tools. So how was BERT trained? So initially, so remember first that, so let's actually kind of go back a little. Oh yeah, that's right. So that's in here. So that's perfect. That's what I want. Right, let me just finish up with those. That slide. So here. Okay, so we discussed it. We discussed that. So the question is, we know that text goes in. Notice that the input here is not embeddings because transformers actually do the embedding inside, right? So we just provide the string, but all the the machine learning, all the neural network layers happen here. It produces these embeddings, a sequence of 512 of vectors of 7, each of which is of size 768. So how was BERT originally trained? There were two approaches to train it because they were just trying to figure out what to do with this machine. They didn't even know. Some text goes in, an embedding comes out, but how do we train it? So the people at Google came out with two tasks. Number one was called the mass language model task, which you've seen me use in the inference examples where we did fill in the blank, right? So that's essentially this mass language model task, which we will talk about a little bit. And then they had another one, a second approach called the two-sentence classification task, which was really interesting. Turned out that one wasn't that significant, but you can see there how they were just spitballing, right? Trying different approaches to train this BERT model. Okay, so that's the idea. So here we have kind of the concept for the mass language model, and simple drawing. So you have an input, which is CLS, a sequence of 512 words, CLS, then let's stick to improvisation in and so on, right? So those words go in. Notice that part of the process in the training is to mask one of the words. That is to say, improvisation is not included in the input, okay? Then remember, there's embedding layers in here that are going to convert this into vectors. Then a whole bunch of matrix multiplications will happen and transformations repeatedly, just like in the GPT. And then at the end, it produces for every, this sequence of 512, notice it produces 512 vectors of 768, these embeddings. And that's kind of where the encoder was in the original Transformers paper, because they were translating from, let's say, English to Portuguese. So then they would use this sequence in the decoder, in the GPT, to actually generate translations. That was it. But here they've decoupled the encoder from the decoder. So what do you do with these embeddings? So notice they just add a feed-forward layer, which is just a normal, like that NN linear that we just did, right? That's all it is. An NN linear with a softmax to a vector that is the size of the vocabulary, that is 50,000. You see that? I only drew it for one, but you would have it for all, of course. And now but you only care about the masked one, which you know which one it is, right? So you're predicting for the masked one what it should be. So now this architecture can totally, right, given this embedding and this feed-forward layer and then softmax plus a vector of 50,000 will give one word that has the highest probability, right? And that's the one that you pick as the predicted word. Does that make sense, guys? So this is how you train it. You would train it with essentially the same sentence as input and output, but it wouldn't see improvisation as input. It would maybe predict, what's a word that's similar to improvisation? I don't know, something else, right? Okay, right. So it produces that word, spontaneity, and then now, is it like improvisation? No. So then that's an error that gets back propagated. The next time, guess what? It does predict improvisation. Boom. Correct? And so now you do that over massive amounts of data, right? The whole internet of text, and now you have a model that can fill in the blank. And this is how we did this last week when I was filling in for certain words, right? So remember, does this make sense, guys? How this works? This is the architecture. So hopefully sometime next week we'll do a baby BERT, kind of this idea, okay? But yeah, that's the masked language model approach to train the model. Just mask a word and then predict it and so on. They tried this other one, which didn't quite work, but actually it's got something very important if you pay attention. So here it's a classification problem, right? Cross entropy type of a problem. It produces a probability distribution over the 50,000 words, and it gives you one word, kind of like a. But this other one is interesting because it's giving you a number, right? So here they created this idea of the two-sentence task. Think about this one slightly, right? So two-sentence task. So how was this pre-trained? Same idea as before. You have an input. Starts with CLS, some kind of a class it's like a placeholder. They were thinking, okay, we're going to use this somehow, right? And so, but they have CLS, and then they have two sentences. So remember that what's great about training these models is that it doesn't require any annotation. You just take text from a book, right? So in the masked language one, you just take a sentence, randomly mask one of them, and that's also the output, and boom. So this is called, what is it, semi-supervised or self-supervised, I believe it's called self-supervised, because you really, a book is self-supervised, right? Somebody wrote it, thankfully, and now you can get all their knowledge about language. The same applies for this idea of the two sentence. This is an important idea. So you have CLS and you can take two sentences, one after the other. Boom, that's one option. Or you can take two sentences randomly from the book that don't follow each other, right? And so you have you know that you took them randomly, so you have the annotation for that. So the is next versus not next. Now you have the information. So I have a CLS, sentence A. The man went to the store. Notice now they're using this other symbol called the separator. That was to give room for the other sentence. And now you can see I have penguins are something. And that's sentence A and sentence B. Notice that here, even though it produces all this embedding, no problem, you're not using it. You don't care about it. You only care about what comes out of this CLS. You can see there's no word that goes through, only CLS goes in, but now you can train it, right, with some data. Here, again, this embedding that comes out is multiplied times a weight matrix, simple NN linear, right, and softmax or some other function, and now you can map it to just be one neuron. We can totally do that, right? We can take any embedding of size 7, let's say 512, do a matrix multiplication, and we have another layer that only has one neuron. And it's a regression value too. And so this one now is just predicting is next or not next. So here it could say 99% is next, which means, 99% is not next, therefore is next is 1%. It's a type of a classification, but from 0 to 1, it gives us a probability. If you think about it, this is the basis for any kind of BERT, BERT model that gives us a score. Sorry, a BERT scorer, as they are called. So this is the basis for any BERT scorer. Okay? You don't train anything here. You only train to give in this kind of format, and obviously it predicts a value here, and you compare it to whatever it is that you want. So now let's go back to this idea of the questions. So I think in the back, you asked the question at the beginning. What's your name, sorry? Basil, that's right, Basil. So in the beginning of the class, you asked this question, right, about how was ChatGPT trained to answer questions really well or something like that. Well, let's take a look. A human, manually first, you get, OpenAI had a lot of money, right? So they hire, I don't know, 1,000 experts, right, in some topic. And they give them, notice here I have sentence A and sentence B, but that could just as easily be question and answer. You guys agree, right? So they look at question, they look at answer, and they go into the BERT, one followed by the other. It doesn't matter if it's next sentence or question and answer, right? And now, well, the human would look at these two. This question then reads that answer, and they're like, yeah, that's a good one. I'll give it a 90 in my score. You see that? And so that manually starts to create some data for rewards. You're going to use that later in a reward type of a application. But it's expensive to have 1,000 people working for you for more than 3 months, right? Even for OpenAI. And they say, actually, these people are no longer providing value. They already gave us a lot of what we wanted. So what do? You automate the process. Why not? Take this BERT. Now, those 1,000 people looked at many sentences that maybe created 100,000 pairs of question, answer, score. Do you guys see that? And now you can easily train this BERT. Here's the question. Here's the answer. Here's the score. Do you see that? So now the BERT model learns to predicts a score for sure. You compare it to the score that the evaluator provided, back propagate, update the weights, and boom. And this is only fine tuning, by the way. Remember that because it's a BERT, we actually had the capability to pre-train it first. So we pre-trained it on a massive amount of data, possibly to do the masking or whatever, right? Why not? And then now it has weights, a set of weights that have been assigned to this BERT, and now we do fine-tuning with those 100,000 question, answer, and score. And what you end up with is a BERT that can actually do the work of humans, right, for this specific task. And so now, sometimes you keep the humans doing some of the work, but you automate a lot of other work with the BERT model. So these are BERT scores. That's an actual term. And they're going to be the basis for our reinforcement learning approach. Does this make sense, guys? Are there any questions on any of these ideas? All right, great. So you guys get it. So that's great. So that's kind of that example there. So let's now oh yeah, I'm sharing. Okay, so now let's go over here, kind of to wrap it up in more detail. So we're going to click on this one, BERT. So if you guys remember, this is, and if you read that 2017 paper, this is the original transformer for language. Yeah, go ahead. Yeah. It's reinforcement learning. It's not annotation. It's reinforcement learning. That score, you mean of looking at a question and answer and providing a score? It's used more in the context of reinforcement learning. It's not annotating a data set for you to then train it in the normal way. The score is a feedback. So they're both working together, like this one predicts, this one scores. This one predicts, this one scores. Do you see that in the loop? That's the difference. Yeah, good question. So now let's just wrap it up. So this is the diagram of the original transformer from 2017. If you notice, like English input, English goes in, Portuguese goes in. It converts it into embeddings, right? N40 by 512, all the layers. which are the same as the decoder layers. There's really no difference. Attention layers, all that stuff is happening there. There's a special kind of an attention in the decoder in translation, but we're not worrying about that. So then all of this, just think of it as it's being transformed via matrix multiplication from one embedding that is 512 to another embedding and so on, right? But if you notice at the end, what comes out is n by 40 by 512 with no meaning, and that is used in the decoder part. So that was split, of course, and this one here is GPTs, like ChatGPT, and this one here is what we're talking about right now, which is encoders or BERTs. Okay, an encoder becomes a BERT when this embedding is used for some kind of prediction. Okay, all right. So that's all this from 520. Okay, but I do have a little bit down here. Encoder-only models, right? So here we have the BERT types of models, and here's BERT. So BERT is an example of an encoder-only transformer in contrast to pure encoders that take a sentence and only produce an embedding. BERT models will add neural network layers called heads, which I've mentioned this before, and that's what that pipe is doing in transformers, just changing those heads, which is just adding those feed-forward layers, okay? So BERT models will add neural network layers called heads after the embedding, e.g., batch 40 by 512, to convert those embeddings into words or sentences. BERT stands for, we've covered this, bidirectional encoder representations from transformers. They were trained using two approaches, which is what I just said. I just wanted to kind of summarize it here in more detail. So here I have one approach. So CLS, as you saw, that's kind of indicating an input class symbol. A sentence, the Princess Mary entered the dark woods of Engar. Size is 512 of this sequence. We mask one of the words, right? Remember that this is converted into embeddings inside. And then finally, this embedding comes out, but we can add any feed-forward layer, e.g. an n-linear, and then produce a probability distribution over the vocabulary to predict the word, right? So that's the same thing I said before, just in a little bit more detail. And here, the two-sentence approach. The first task BERT was pre-trained on was the mass language modeling approach. This approach is summarized in the previous figure. Here the BERT model receives the same sentence as the input and output. See how that's similar to an autoencoder, right? So that you can see the thought process. So here the BERT model receives the same sentence as input and output. Some tokens are masked, and the model needs to learn to predict those masked tokens during the training process. The second task BERT was pre-trained on is a two-sentence classification task. The figure below summarizes this approach. Basically here, two sentences are given to the BERT model as input. The model trains to predict if these two input sentences are sequential, which means they are also related, or if they are not sequential, therefore unrelated. But we can change that meaning, as I've mentioned, to good answer, bad answer. Lots of flexibility. So it learns to, if there's unrelated. BERT was originally developed by Google, and there have now been several other versions that were developed. They all follow the same naming convention of being called Roberta, Albert, Distilbert, and so on. And here's the architecture again. So you can see we have sentence A, sentence B. We can mask it. That goes in, gets embedded, and then we ignore essentially other outputs and just worry about predicting or producing a score. And that becomes a BERT score. All right, so now that's, kind of the theory of this, just to give you an idea of how it works. As I said, later on we'll maybe do a baby BERT, very simple. But let's jump ahead now to, or go back to transformers, right? And the transformers library from Hugging Face. And we're going to start now that we have some theory, some understanding to use some of these tools, right? The BERT scorer in particular, right? And so on. Are there any questions before I move on? Nope. All right, great. So we've covered that. So now let's go back to the table of contents. And I have a few scripts that I put together. I'll close this one. Okay, so let's go here and code. So this is the last part of this section. If you notice, after that, essentially, the homework, one of the homeworks is going to come up. But let's take a look at code. All right, so here I provided several examples. Ultimately, the goal that we have here is, besides understanding, is that we want to train, we want to, we want to fine tune, let's say, a BERT, and we want to apply reinforcement learning to fine tune a GPT. Okay? So that's the essential mechanism. So here in this Hello World GPT-2, I'm giving you the code to use a GPT-2 with transformers. Okay? This GPT-2 is what you can use for this reinforcement learning task. Okay? So let's start there. So Hello World GPT-2. Okay? And you will see this is essentially how we can bring in GPT-2. As I said, I'm using GPT-2 because it runs, because of memory issues. If you can, have more computing power, have a professional version of Colab, those kinds of things, right? You can use a better GPT-2. But I'm going to use this one. So let's go ahead. First of all, this is my, our GPT-2 from Hugging Face. Remember, this is not like in 520 where you pre-train a GPT and that was it. This was actually trained by a company with a lot of GPUs and massive amounts of data. And it's still not the greatest GPT-2 because it's only pre-trained. There's no fine-tuning, no reinforcement learning, and it is smaller. It's 12 blocks, essentially. So let's go ahead, first of all, and do this. Go to Colab. Notebook. Cool. So again, our library for a lot of these tasks is going to be from Hugging Face, transformers. Notice we're using pipeline, auto tokenizer, trainer, training, arguments. Okay, so let's run this. Let's give it a second. All right, here we are. Okay. So now, there's a lot of topics. So obviously, when we talk about something like an autoencoder is pretty simple, right? Some code, it's got like a specific layout, a goal. It's easy to understand. What we're trying to do now is by definition hard, right? Making a chat GPT is hard, right? So, but we're trying to, so there's a lot of moving parts. So let's kind of think about this. We are going to have a GPT-2, that is not something you pre-trained, but someone else pre-trained it. It's got a lot of information there. And then we know we're going to learn now that we have tasks like fine-tuning and reinforcement learning. Ultimately, what we want to do will be one of your assignments, the main one at some point of this sequence will be that we want that to make that GPT-2 funnier, or we want to make it more spammy, or we want to make it, write sad movie reviews, or be scary. You know what I mean? That, or more toxic. I mean, that's I guess it's okay, but as a homework assignment, right? You know what I mean? So this is what the goal will be. So how are we going to do that? That's the question, right? So we have to understand concepts of reinforcement learning, fine-tuning. We're going to need something to help us provide reinforcement learning because we can't do it manually. So then maybe a BERT and so on. Do you see that? So that's essentially, and the BERT is going to be a BERT score that maybe somebody created a BERT score just to find offensive language, right, in text. That's a possibility. Somebody just created it for that specific task, but we can repurpose it as a reward function to make our GPT be less offensive in our case, right? We can flip it somehow. Got it? So this is kind of the whole architecture that we're going to need, and this is going to involve lots of things. Transformers, this library, TRL, another library that we're going to look at, and so on. All right? So don't lose sight of that goal. Right now, I'm only introducing the very basic GPT that you can use, GPT-2. Feel free to use others. I'm not going to do any training or anything like that. I'm just going to use it in inference mode. But I want to provide this for you so that you have actually something that you know you can use. All right, so a max length of 150 return sequences, about 2 sequences. So it can generate, 2 answers if you will. All right, so those are just parameters. And then this is just a function to return examples. So it's going to generate examples. Okay, so notice here we're going to have a generator, we're going to have a prompt. So somebody mentioned the word prompts, right? So that becomes like the term when we're using GPTs now, although this is not a prompt engineering class, but our inputs to the model become the prompts. So we have a prompt list, for prompt and prompt list. Notice generator gets a prompt and all these parameters, and it provides results, okay? And then those results, we create a dictionary of the results, right? Answer and generated text and so on to keep track of things. And then that's it. It's just a little function to handle creating the dictionary, a list of prompt and answer. Does this make sense? This little code here. All right, so I click on that. It's not really, you could do this manually if you want. It's not meant to help. All right, here we are now. So remember last week, I don't know if I did any GPTs last week. I believe I did some BERTs. But the whole idea was we used the Hugging Face hub where we have these models and the tokenizers associated with them. So we always download a tokenizer and the model. So we're going to bring it down, and then we can use things like pipeline, right? This function that allows us to add heads and things like that for specific tasks. Notice here, it's going to be a text generation task. So first of all, we're going to get GPT. So this is GPT-2. For me, as I'm lecturing, definitely I want to use the smallest thing I can find. I encourage you guys to go on Hugging Face, try out a more powerful GPT if you can, okay? That's definitely my recommendation, but just be aware that's going to be a massive amount of memory. So the model name GPT-2, remember, if it's like a default model in Hugging Face, it doesn't even have a user, it's just a default. We invoke pipeline, we say text generation, and we assign GPT-2 to it. Notice it starts to download it. We probably should have this in GPU mode at this point because even inference does require a little bit of GPU. I don't know if you guys knew this, that actually OpenAI loses more money on inference than in training, right? So all those GPUs, because, for instance, for logic questions where it has to generate a very long chain of thought, and that's a lot of words, that's a lot of money. So they're actually losing money. I don't know if you guys know this, but OpenAI hasn't made money. All right, so yeah, so we have our GPT-2 there. So there you are. You now have definitely a GPT way more powerful than the one that you pre-trained in 520, right? So this is definitely more powerful, and it may not be still as good as you would like it to be. All right, so now let's go over here. The tokenizer as well, so you can download that auto tokenizer, GPT-2, just the names need to match. And now I'm going to have essentially, so in this list to answer, list of questions, I have one question: when will it snow this week? So I use the function generate examples. I give it the generator and the list, and I ask it to say something. Okay, you can see it's doing some inference. And these are the, notice there's two answers because we asked for two answers. Right here. All right, here we are. So let me grab these. That's a long answer. Okay, here we are. So let's now analyze. So this is our GPT-2. Our question or prompt was, when will it snow this week? The answer was, and notice, remember, it always outputs the input as part of the answer. And it says, we'll have to see. A few weeks ago, I posted a link to several news articles about the snowstorm in the Bay Area. How does it know we're in the Bay Area? My first take was that it would probably be a warm day, but it turns out that the storm was actually cooler than I thought it would be. So we'll be seeing snow in the Bay Area this week. What do you guys think? Compare this to 520, right? So you trained a GPT then from scratch. Is this one better or worse? It's better, right? So it's got better grammar probably. That's one thing I noticed, right? So it knows how to construct a sentence. It's essentially, it's a hallucination as they call, right? So it hasn't made any, I mean, it says it wrote an article, I think, or posted a link. It probably made that up, right? But that's the GPT. We look at the other answer. It has snowed in several locations this week, which makes for an interesting story. In late June, the snow was so heavy that snow was falling on a bridge over the Bay Bridge. This prompted a storm surge to the peninsula and caused a minor power outage and so on. So you can see the grammar looks good, looks like a good answer, but it's still not something, if you're a user using ChatGPT and you get these answers, you're not going to be too happy, right? And so that's because this is just a pre-trained version. Now you would get a question to answers. You have to start fine-tuning, providing feedback, which will update the weights, and then you start to get a better GPT. Does that make sense? Now, obviously, that's a hard thing to do. I'm not saying that your goal is to create a chat GPT that gives great answers about everything. Instead, what I would want you to do in one of the, as we get towards, the actual goal, I would want you to fine-tune the model with reinforcement learning so that the answers are funnier somehow, or more spammy, as I said, or more horror or something. Does that make sense? So that's the goal. It's not going to be something massive, but I should be able to tell by looking at the text, oh yeah, that kind of looks like a scary word or a spammy word or something. That's as far, that's what you'll get essentially, in your output. Does that make sense, guys? All right, so I have at this point given you GPT-2, right? So you have this model now, play with it, and just be aware, this is something you can use. Or if you get a better model, that's even better. Great. So we did that. Any questions on this before we move on? Perfect. All right, so now that we have a GPT, we have to think of the idea. So we want to nudge the weights a little bit so that it provides better answers and all of that. So how do we do that, right? So we have to continue the process. This is a pre-trained model, so we have to understand how to do fine-tuning of both BERT and GPTs, and then we also have to understand how to do reinforcement learning of GPTs with BERTs. And that's kind of the plan. Now, there's two approaches that you'll have in that homework. You could actually take a BERT and fine-tune it to be whatever you want it to be. You could, in theory, train it to be funny by collecting data, providing rewards, all of that. Or the simpler solution is for you to use an existing BERT from Hugging Face. Do you guys understand that? So I'm not making it a requirement that you have to create the reward function. You can just take one from Hugging Face. One thing, though, is that we did see that example of zero-shot learning, if you remember. So remember that example, and that is something that you will have to do. Try out an existing BERT versus a zero-shot one. But I'll describe that in the assignment. Okay? All right, so we did this. Now let's go back and try other things, other concepts. One of the things we need to cover is the BERT score, right? So that's something we want to take a look at. So let's go back to Brightspace. I'm going to go back to the table of contents. So remember, we're in this module, and we're just going over the code. We've covered this example. I have a few examples here. As you can see, they say GPU required. And these will be examples of fine-tuning. So this is a fine-tuning example, fine-tuning a BERT, and so on. So these are the topics that we have to start to get into. The only issue with these, we still use transformers, but we're going to have to learn the format of things. That's unfortunately the bad part of using a library, right? We're kind of fixed to however they do things. And so that's going to be the challenge for us, is we always have to get that correctly. We have to take our data, for instance, and format it in the way that they want it, and then load it. So we'll get to that. All right, but just be aware that's the next set of examples. But there's one more thing I want to cover before we do that, and that's here. We're gonna to wrap up the concept of embeddings, right? I want to wrap it up with this example that I put together. This is called a sentence similarity and embeddings script using something called Flare, which I think was made by Meta when John LeCun was there as director. So let's take a look at this one. So again, we're going back to this idea that words are embeddings, right? In transformers, we take a sentence that becomes a sequence of embeddings, right? And we already learned in the previous lecture that embeddings are just points in a vector space, and then we can do arithmetic already and also calculate distance metrics. We did that with the autoencoder. You see how all the concepts are kind of related. They always go back to the same place. So we're going to take this example where we have similar and dissimilar sentences, use embeddings of some kind, and try to measure some score of between the sentences. So let's go ahead and do that, and you'll see at the very end I'll be using a BERT-based NLI model to do this. So a type of a BERT score. All right, so let's go ahead and grab the libraries. You can see a lot of libraries. We may need to install also some things like Flare. So here I'm using Pandas, Torch, NumPy, and then the library Flare. Okay. Now this library was created essentially to play with embeddings, to take them outside of the transformer, take the words, represent them, and then do calculations like distance metrics. So we have Flare data sentence from Flare.embeddings. We're going to bring in word embeddings, document pool embeddings, RNN embeddings, transformer document embeddings, and sentence transformers. So you can see several approaches that have been created from the original word-to-vec type of approach. Notice this one, RNN embeddings, is essentially using a recurrent neural network all the way to state-of-the-art, which is what? Transformers, right? Like a BERT. All right, so let's run this one. So it's got it's missing a library, Flare. So I need to install it. So in the libraries, let's give it a minute. All right, it finished. Okay, so now let's run the libraries. What I like about this example is it's almost like the history of this for the last 10 years or so, right? It kind of shows you the results with word2vec versus where we are today with transformers. Okay, so let's take a look. Should be pretty straightforward. So I have a list of sentences. Okay. So I have similar sentences. So for instance, these are going to be pairs like the black dog walking beside a pool, and versus that's sentence one. Then sentence two, a black dog is walking along the side of a pool. You see they're similar, right, in meaning. Then similar, a blonde woman looks for medical supplies for work in a suitcase. The blonde woman is searching for medical supplies in a suitcase. The third example, a doubly-decker red bus driving down the road. A red double-decker bus driving down a street. There is a black dog jumping into a swimming pool. A black dog is leaping into a swimming pool. See, there's some. All right, so these are the similar examples. Okay, for the data. Remember, we're going to do embeddings for these. So this is we need a good embedding mechanism. So we can print the data. Just an example of it using pandas. See that there? So sentence 1 and sentence 2. Now we have another list, which is going to be a list of dissimilar sentences. So here we have, for these example, these pairs, a little girl and boy are reading books versus an older child is playing with a doll while gazing out the window. So they are now dissimilar, right? Dissimilar. 2 horses standing in a field with trees in the background versus a black and white bird on a body of water with grass in the background, and so on. So you guys get the idea, right? So the first set was more similar. This next set is dissimilar. But so we've been talking about embeddings and how they can be used as vector spaces to represent all these words, right? And then we can use them to kind of understand meaning or understand similarity and how measure the level of similarity between 2 sentences. So now that's what we're going to try to do. I'll skip this part. I'm going to create a little function here. And I'm going to create an evaluate function, and we're going to try several methods also. Okay, so this one essentially takes sentence 1 and sentence 2, right? Assumes that we have a property of embedding for them, and we calculate what is called a cosine similarity. A cosine similarity function which outputs a value between 0 and 1 of how similar 2 things. This is essentially just applying math to it. No, nothing else, but this depends on having some embeddings for S1 and S2. So the function will take S1 and S2 and calculate the difference. Okay? So that's that function. Take a look at this one. So this function here uses sim, the previously created function over here, right? So it evaluates embeddings for a given list of sentence pairs. So we've got the embeddings and my list. This is like the technique, right? So for S1 and S2 in my pair list, so we graph sentence 1 and sentence 2, right? And we this sentence here is a library from up here. Yeah, so from Flare, right? So it'll take the sentence and format it. Okay, so it takes S1 and S2, runs it through these functions, and just updates it. Then we take S1, and it's probably like, imagine it's cleaning the sentence, removing dots and things like that. Then I take S1 and S2, and I'm going to use whatever technique I've selected for embeddings, and I'm going to embed S1 and S2, essentially creating vectors for each of the sentences. Then I'm going to run them through the cosine similarity function to produce a score. So this essentially implies that the metric is the same, but the embedding mechanism is what matters. Do you guys see that? So that's really what's going to make the difference. The metric is the same. If we use a transformer, that may produce a better embedding than using word2vec. Okay, hopefully that makes sense. And then we have the scores here. So I'm going to click on that. I'm going to add a few more. So now let's start with, we have here glove. Glove was a technique that was very popular. It was like word2vec, but better. It's like a, this was back in the day. Remember, these were just, for every word you had an embedding. That was the approach back then, not tied to the transformer itself. So let's take a look at this one. Oops. Okay, so glove embedding, so word embeddings. So it uses the word embedding technique, but the glove version. Okay, so this is popular. Okay, and then glove embedding, we use something called document pool embeddings to create the approach that we want to use. So you can see this is pretty big because it's, it was a lot of data that was trained beforehand. Okay, and again. Oh, this error with Jensen. This, I think I ran this. Let's give it a minute. All right, so that worked. So let's try it again. It worked, right? Okay, so good. So that means I'm using essentially the embedding solution from like 2014, 2015. That's where I am. I'm back in time, 2016, let's say. This was very popular. Let's see if it works. Okay, so I'm using glove. And now what I have to do is evaluate, right? So, okay, so glove just, it averages the embeddings essentially. So every word has an embedding of 512, they're just being averaged. Here I evaluate using this technique, glove pool embeddings, and I'm going to evaluate the sentences in similar and also the sentences in dissimilar. Okay. And so this is saying so the score is not that great. It should be like this one should be high. This one should be a bit lower. Okay. So let's try another one. This is GRU. This is based on a recurrent neural network. But again, it's trying to create an embedding. So just like we're creating embeddings with the autoencoder in the previous example, now imagine I'm going to create embeddings with this thing called a RNN embedding approach, GRU. So let's use this approach. So that loaded fine. We're going to run it again. So what do you guys think? Now the spread is a little bit bigger, I think. This was 98 to 94, so that's 4, right? So it's evaluating how close these. Yeah, these are closer. These are less close, right? But it's still difficult because they're, there's 98 to 94. This one is 97 to 93, a bit bigger spread maybe, or the same, about the same for dissimilar. So our expected value should be that this is like 98, and then this should be much lower, right? Like 30 or 25. So let's try another one. So notice here in this evolution, it's like we were doing word to vec, then we're using RNNs, right? Let's see what else we have in store. Now the next one is to use a transformer. So an advancement in the technology. So this is a BERT document embedding using a BERT based on case. That's an embedding machine. Okay. We compare them again. Okay. $90 to $92, actually worst, right? Actually worse. And it's a transformer. We would expect it to be much better. But we are using a BERT based on case. It's essentially, you can say you're just using a pre-trained BERT with no fine-tuning. Do you guys see that? So now what do we need to do? We need to have a BERT, but a more specialized BERT. Okay? So that should be the last one we have. This is this one. SBERT embeddings, a sentence transformer document embedding using a BERT-based NLI mean tokens, right? So this one's a little bit more specialized as a model than this one. So let's run it. Okay, it's loading. Okay, and now the moment of truth. So we go over here. We perform the same evaluation. And now we get 97 versus 21. Do you see that? So this is the evolution of what we're doing. We're not even generating text. We're not generating scores exactly. We're just generating embeddings, right? Goes back to this idea I told you, BERTs are embedding machines. The whole discussion today has been about embeddings, from autoencoders all the way to BERT models. The power is there. So you might, this might seem trivial, but achieving this 97 versus 21 took a lot of work, right? Before, everyone was just, living in a world where these were the answers, 97 to 93, right? Not clear cut. And as you start to leverage the large language models, then you start to get, really, really good results. Okay? All right. So, yeah, so that's essentially the discussion on embeddings. If you notice, that was a big topic to cover in the course. And so as a stepping stone towards more details in BERTs and reward functions, we've covered this topic, and this wraps it up. So hopefully that makes sense as far as what embeddings are and how they can be used. They're essentially vector spaces. Okay? So in the next class, so we'll finish with this topic today. So we covered this one, but let's just take a look at what we have left. You can start playing with this if you'd like, but we are currently, go back to table of contents. We finished transfer learning intro and Hugging Face transformers. We covered autoencoders. As I said, look for a homework related to this by the weekend. And we are currently here. I wanted to focus today just on embeddings, kind of the theory of everything, and introduce GPT-2. So I've given you GPT-2 now, which you will be using for your homework assignments. We covered this sentence similarity and embeddings, and now we are ready to go into this section, GPU required. So next week, we'll start looking at these ideas of how to fine-tune these models. Obviously, we're going to need transformers for this, so we're going to start to learn that process of how to update the weights of the models. Does that make sense? So that's the plan for next week. All right. Yeah, so we'll stop here for today, and please look for the homework by the weekend.